Hey everyone, so welcome to Hudson and Thames' very own reading group. So if you're interested in this reading group, please go and click the link down below and join our reading group. So what does the reading group consist of? So here we explore papers and we ask questions, we gain knowledge. So today we'll be exploring a paper from the Journal of Portfolio Management. So this paper is about enhancing time series momentum strategies using deep neural nets. Okay, so let's get to it.
Just to correct Michelle, so it's actually the Journal of Financial Data Science, but it's the same journal company that owns both journals. But cool, no worries. For those just joining, my name is Jacques Dubé. I'm the CEO of Hudson and Thames, and I'll be joining Michelle today, also to add kind of insights and discussions. I recently just came back from the QuantStrats conference here in London. It was held yesterday, actually, and so the people who wrote this paper is the Oxford Man Research Group, and they were presenting a follow-up paper based on this, and I got to ask them some questions that I didn't really have the answer for when we were implementing this paper and building it, and so I'll try to inject some of that knowledge as we go through the presentation.
Awesome. So who am I? So I work for Jacques. I'm also a quant researcher, and at Hudson and Thames, as I said, we have this awesome reading group, and we're here to gain knowledge. So what I'll do today is I'll discuss momentum strategies. So you get two different types explored in this paper, and then I'll also talk a little bit about how to construct a trading signal in the traditional way, and then some machine learning extensions thereof. So this paper provides an alternative solution to calculating a position size, and it proposes 4 architectures using this deep momentum network. And what we'll do is we'll look at the data a little bit, and then we'll see how these architectures perform, right, with some performance evaluation metrics. And then lastly, we'll look at cumulative returns across these different models. Cool. So what is a momentum strategy, right? So investors buy securities, right, when the price is rising, and when this price is peaked and it looks like it's going to drop, investors sell, as basic as that. So how do they do this? How do they know? So they use past returns, right? And they use that to predict future returns, basically. And in this paper, they quickly give a rundown of a cross-sectional momentum strategy. And all this is basically is comparing the relative performance of a pair of securities with another pair of securities. So it's based on buying relative winners and selling relative losers. So what you could do is you could take a universe of stocks and you can split them into a top decile and a bottom decile, and you can trade them against one another, for example. But this paper focuses on time series momentum strategies, and this is basically just a asset's own past returns, and you have a whole portfolio where you look at past performance of each of these securities separately. Okay, Jock, cool. If you want to add anything?
Yeah, so I just want to kind of highlight why we picked this paper as well. So first of all, Oxford Man Research Group is awesome. They come up with excellent research. It's really well written, the papers that they write. But the reason I love this paper so much is that it also gives the math for you to see, how do you run a backtest? So they have equations for it. If I remember from the paper, it's equations 16 and 17 show you how to run a backtest, and they also introduce, so they provide the landmark papers for momentum investing. And so when I started my early career, I started off on this cross-sectional momentum, particularly 2 papers. So the landmark paper in the field there is written by Jagadish and Titman, and they basically describe that, hey, you create a long-short equity factor portfolio where you rank stocks based on their 12-month returns. You rank them top down, you go long the top 10 stocks, and then you hold them for 3 to 6 months, and then you rebalance the portfolio. And that does really well, as it turns out. A follow-up to that paper is Gary Antonacci's dual momentum, which is something I've also implemented. And so if you're thinking of building these cross-sectional momentum strategies, I think that's bread and butter. I used to work as a trader before here at Hudson and Thames before I started running the company. And if I'm joining a trading desk, the first thing I always build are these momentum strategies, because they're really simple to implement. They make money, and it's a good revenue stream before you start building more complicated things. And so cross-sectional momentum, a big part of that is for equity investing. And then when we talk about time series momentum, that's really just kind of like you've got one asset and you're trying to figure out like when there's momentum in that asset, and then you're trying to trade it. And so the toy example I always give here that you'll learn in like trading 101, I guess, on the technical analysis side, is like a moving average crossover strategy. Like, hey, the fast moving average crosses above the slow moving average, that's, you know, a buy signal. And when, you know, the fast crosses below the slow moving, that would be a sell signal. So that's a type of time series momentum strategy. And so yeah, just filling in some of the blocks there. Thanks, Michelle.
Awesome. So let's look at constructing a trading signal. And there's a traditional way of doing it. And then there are also some machine learning extensions. And this paper as well is a machine learning extension. So the traditional way, as I said before, you use past trends to predict future trends. And then you have to manually specify how you are going to get to your trading, your position sizing rule. And for machine learning extensions, what they try to do was they try to include things like regression and binary classification, right, to estimate this trend in data. But there's still a manual specification that's needed, right, to get to your position sizing rule. So what this paper proposes is a method of directly calculating your position sizing rule. So no need for calibration and thresholding to get there.
Yeah, and so adding to this, I mean, again, this paper is showing really nicely from first principles how people generally build trading strategies, right? I mean, in a trend following strategy, the first part of the strategy is we need to identify, is a trend present, and like perhaps maybe the quality of that trend or how strong the trend is. And then the second part of that is, okay, well, you know there's going to be a trend. How do you size the position? And so that is traditionally kind of, this core idea of separating side from size. And so, today actually we have a reading group, and we're going to be talking about our paper on meta labeling. For those of you familiar with meta labeling, it's a secondary machine learning model that sits on top of any primary investment strategy, and it helps you to size positions. And so it's just, again, building on this idea of separating a side forecast from your size forecast. And so what's quite unique about this paper, it introduces this architecture called deep momentum networks. And what the authors are saying is that, hey, let's train a model to not only just learn the side of the trade to take, but to also learn the size and to optimize for like Sharpe ratio or max returns. And this is a really cool idea. In fact, I think it's a novel idea. I haven't seen anybody else do this in this way. And I also think it's a pretty cool idea for meta labeling even. I mean, it's very different to meta labeling in that it's doing everything under one model, where meta labeling was separating the side and size. But this idea, and you're going to see it in a second, that Michelle's going to introduce, is this idea of using the Sharpe ratio as part of your loss function. And so I like that idea, and I wonder, hey, can we add that into meta labeling and train the secondary meta model with a Sharpe ratio, and then optimize for that? But anyways, I'm jumping a bit ahead. Over to you, Michelle.
Awesome. Yeah, so the reason the authors did this was so that they could actually compare trading rules with one another. So within the same function, you'd like to calculate the trend and the position size. And how you do this is, well, you have to directly optimize performance metrics. And in this case, as Doc said, we have two different loss functions. So we have average returns that we're optimizing for, and then also the Sharpe ratio. And then these loss functions are included in the output activation layer of the neural net. So we have a simple tan function, right, that calculates the position size, and then we include these loss functions.
So maybe, Michelle, you've just implemented this paper for us. Maybe you can just elaborate a little bit. Like, let's just use a simple example. So, we've got the input layer, which is, passing the data through. Then we have the hidden layer, the first hidden layer, and then we have the output layer, right? So what this is saying is the output layer should have these loss functions, but the hidden layer is still going to have like a sigmoid ReLU or tanh loss function, right?
Yes, exactly. To calculate that position size directly. So in between -1 and 1.
Perfect. Okay.
Cool. So this specific deep momentum network has 4 different architectures, but all 4 of these have to, perform the same thing. So they have to generate different predictions. So it can be either the expected returns, binary probabilities of its classification, and then direct positions. Cool. So The first one is a lasso regression. So this is the simplest model, and it's basically just augmenting your loss function, so adding a penalty. And we have a multi-layer perceptron. So it's a little bit more complex than the lasso regression. It's basically just a 2-layer neural net. And then we have a more complicated model, so a wavenet. And this is a CNN, so convolutional neural network. And we increase the amount of historical information while we train the model in this architecture. And then the last one is just the LSTM. So this is long short-term memory. And here we use a cell state to retain past information, but we also have something called a forget and an input gate that we use to update memory when we train the model.
Cool. Yeah, I think the one thing here, I don't know if it's on the next slide, but if you read the paper, you'll see that they highlight that you don't need something as complicated as a wavenet. In fact, the wavenet doesn't perform as well as the other models. And so I just want to highlight that, more complexity does not mean a better model.
Yes, and we'll see that in when we look at the performance metrics as well. Okay, cool. Just a quick look at the data. So we're working with futures contracts, and they're all ratio adjusted. There's 88 of them, and they include things like commodities, fixed income, and currency futures. So here's an extract for you guys on the right. And then, it's from 1990 all the way to 2015. And then something important just to note, so these 4 architectures, we're comparing them against benchmark strategies, and there are 3. So when you use a long only, right, scaling for volatility, and then we use the signal as is for returns, and then we also have, and the paper gives a full explanation of this, an MACD signal.
Yeah, so the only thing I really want to add here is that I think of quant investing quite different to fundamental investing. I think I have friends who work at really big funds like Citadel and Millennium and DE Shaw and places like that, and the people there who work on fundamentals, they deeply understand what moves the price of the asset, and what fundamental information is going to cause what kind of price moves. They understand those processes exceptionally well, and I think if you're coming from a quant perspective, there should be this. I don't think you can compete with them on that level. But the one place you can compete, for example, like let's just say it's a gas desk, right? They may know the fundamentals of gas phenomenally well, but because they're fundamental analysts, they don't necessarily know the fundamentals of, say, I don't know, corn really well. And so one of the benefits we can do with quant investing is we'd rather take like a top-down approach rather than bottom-up. So bottom-up kind of being like, we'll take gas, we'll understand the fundamentals extremely deeply, and then go from there. With a top-down approach, it's more like, what kind of like anomaly can we exploit in gas contracts? And then, can we exploit the same anomaly in other contracts? And so a major benefit of quant investing is that we want to kind of diversify and extract the same anomaly across different asset classes, across different securities. And so you can see in this paper, they already do that, right? So they're doing a whole bunch of different commodities from agriculture. Looks like they've got metals in here. They've got energy. There's livestock, and then they do equities and fixed income. So it's a very diverse portfolio, and we're going to try to exploit this momentum anomaly across all of them. And I think in that space, you have the upper hand.
Yeah. So what we'll do now is we'll take this data, and then let's look at the performance. So firstly, let's just look at the raw signal output, right? And then lastly, let's look at it rescaled for volatility. Okay. And we'll also compare especially this LSTM when it's scaled for volatility. So the first thing to note is our multi-layer perceptron, right? So if we look at the expected return, we can see that, has the highest return across the board. And if you look at the wavenets, as we said before, it didn't have, it didn't outperform any of the other models really. And we can see that with the Sharpe ratio as well. So the MLP and the linear model all have greater Sharpe ratios, and the LSTM. So that's quite interesting. Jock, if you want to add something.
No, I mean, that analysis is apt, right? Is that more complicated models don't necessarily mean better performance. Now, the Oxford Research Group, they have gone and, this was kind of like the landmark paper for deep momentum networks, this architecture that they're proposing. They then went on to write a number of papers after that kind of build on it, so they've got like transformer architectures for this that do even better than, this model here. And so this is just the landmark paper. And so their latest paper that I, was lucky enough to be with them in the crowd while they were presenting on it, is very complicated. But the benefit to that is they actually have an open source GitHub repo where they have all the code for that I think will interest a lot of people. You just got to Google it. I think it goes, I mean, I can't remember the name of the top of my head. It's like Transformer Networks, but if you just go Oxford Man Research Group, Transformers, Deep Momentum Networks, I'm sure the paper is going to come up. And if you check out Google, if you check out GitHub, you'll find the repo there. And then that repo will have like the latest architecture, how they add the loss functions, and everything that you're looking for. Yeah.
Okay, awesome. Thanks, Doc. And for just something to note as well, the LSTM. So if you look at the one that was adjusted for the Sharpe ratio, we can just see like the performance right across the board. And we can see it has the lowest volatility, lowest downside deviation, and then maximum drawdown is also lowest. And then we have, a Sharpe ratio that's close to 3, which is very, very good. So optimizing for for the Sharpe ratio over here definitely increased performance. Jock, I can move on to volatility, right?
Yeah, I think so.
Cool. Okay, so let's rescale for volatility and let's compare. So the moment we optimize for the Sharpe ratio with MLP, we can see that yes, downside deviation still performs well, but that LSTM again had the highest expected return, and again the smallest maximum drawdown and the highest Sharpe ratio. And something that's interesting to note is the Sharpe-optimized linear models also outperformed, right? So if you look here, over there, outperformed our benchmark models, which is quite interesting, and it's the simplest architecture mentioned. So yeah.
Cool.
Awesome. And then the last thing I just want to mention is cumulative returns. So we can see that our LSTM, so that's that black curve over there. Then we have our multi-layer perceptron, that's the red one, and then the wavenet, that's the blue curve over there. And then our linear model is, I think, all the way over there. But yeah, we can just see that the architectures proposed, in this paper have high cumulative returns than your standard linear and classification methods. So yeah, it just goes to show that the way that they calculated or predicted the position size using your Sharpe-optimized or average return loss function, yeah, it performed really, really well.
Yeah, I think so. One of the things I just want to highlight here, which is also really cool, is that, they provide 3 benchmark trading strategies for trend following, right? They do, well, a long only, so I don't know if I'd use that as a strategy, but the sign on the return and the MACD, those are 2 other totally separate investment strategies. So what's cool about this paper is that, I mean, this paper really adds value, right? If you're thinking about things that really grab your attention, like what is things we look for as traders in papers, and we look for papers to give us trading strategies. That's the number one goal, although we never find that. And then the second goal is like, okay, what kind of ideas can we use as inspiration to build trading strategies? And what's nice about this paper is it gives us 2 other trading strategies, and then it shows us, oh, here's 3 or 4 different models that kind of like use that as inspiration and build another trading strategy. So this paper is just like super information rich with things that I think traders are looking for in a paper. And so you'll notice that the performance here is exceptionally well. It doesn't include costs. And when we replicated this paper, we found that because you're using a neural net, right? And first of all, it's not a convex optimization. It does get stuck in local minima. And so because of that, what happens is every single time you run this model, you get a different kind of like P&L curve, this cumulative returns plot. Now, when I was in the crowd yesterday and Stefan Zohren was presenting on this paper, I was lucky enough that I could ask him the question of, how, like, first of all, is that true? Did you guys find that your P&L curves are different every single time you run the model? And then how do you adjust that? And so he said, yes, absolutely, indeed, they are different every time they run the model. But what they did is Now, I mean, I'm paraphrasing what he said, but what I remember is him saying, they would take like 5 runs of the model, and then they would ensemble that, and then kind of, use that ensembled value for, what the position size would be, and that made it a lot more stable. And so, yeah, we're looking at 1 run here, but just note, if you run it, it's likely not to look exactly like this. I mean, first of all, they used tons of different commodities, right? So it's a huge project for you to set up if that's something you want to do. But I would recommend like maybe starting on just a couple of futures contracts, building a portfolio with them, and then, getting this performance. Our early results are saying that, this is working really well on equities. So that's something our engineers tested out this week. So it looks like it works well on equities. We're still testing it on other assets. But it's just such a cool idea of like incorporating the Sharpe ratio as a loss function.
Yes, definitely. And this is the last slide. So thanks so much for joining, everyone. Perfect.
Thank you, everyone. Hope we see you in the next one. If you like this lecture, please do sign up for our reading group. It's all the information is on our website. We usually go through a paper, so we'll pick a paper. If you are interested in this paper, you can just Google the name of the paper. It's published in the Journal of Financial Data Science, but this paper in particular is open access, so you don't need a journal subscription to get access to it. So we're starting with our favorite papers and high quality papers. Usually that includes, we read through the papers, we highlight, we leave comments in the paper. We then send those annotated notes to everyone in the reading group. They then go and read it before our session that we have on a Friday afternoon, 4 o'clock London time. And then with that, they can send us questions for like where they'd like the discussion. So this time, Michelle and I are recording this, after the fact, after we've actually given the reading group. But usually there's a lot of discussion in between here where people are asking questions and we talk about it, and ideas flow. And then we record the lecture, and everyone in the reading group gets those recordings. And so I think we'll probably publish this video publicly on YouTube. This one and maybe another video. But then after that, all the videos in the reading group are all private. And so the only way to get access to that is via the reading group. But perfect. Let's end here on a natural note. And yeah, I hope to see you guys all very soon. Thanks, everyone. Cheers.